Thyristor is a family of semiconductor devices, i.e. SCR, Trioc, PUD, RCT, GTO, etc. The oldest member of this thyristor family is SCR, silicon-controlled rectifier. Due to the vast use, the word thyristor has become synonymous with it, and hence, the term thyristor is used for SCR. Compared to transistors, thyristors have lower on-state conduction losses and higher power handling capability. On the other hand, transistors generally have superior switching performances in terms of faster switching speed and lower switching losses. Consider the following circuit and observe the switch. Thyristor is just like this switch before the gate signal is applied. When a triggering signal is applied, the switch turns on and current starts to flow. An SCR is represented by the following symbol. It has anode and cathode terminals, like diode, with an additional terminal known as gate. Gate is the control terminal, and triggering signals are applied at it. On the right, the VI characteristics of a thyristor is shown, clarifying that SCR conducts in first quadrant only. When a gate signal is applied, an SCR is made sufficiently forward biased to cross holding current limit. It starts to conduct. Once in conduction state, it continues to conduct even if the gate signal is removed. Special techniques are employed for turning it off, known as commutation. Let us now learn the working of thyristor by considering its internal structure. Thyristor is actually a 4-layered p-n junction device with 2 p and 2 n portions. Without the application of any voltage, it has 3 diffusion regions. Now, if we apply positive at anode with respect to cathode, the junctions J1 and J3 become forward biased, while making junction J2 reverse biased. It will remain in this state until a positive signal is applied at the gate terminal. So, when a positive signal is applied at gate, the junction J2 turns to forward biased state, and current starts to flow. On removal of gate signal, the current continues to flow as charge is drifted from anode to cathode. If we observe the internal structure of thyristor closely, it will be revealed that it is actually made up of a PNP and an NPN transistor, such that the collector of first is connected to the base of second. Gate is connected to the base of NPN transistor. On application of signal, the NPN transistor conducts, sending a signal to the base of PNP transistor, which in turn conducts and send another signal to base of NPN transistor. Hence, the process continues. Rectification is the conversion of AC to DC. Here is the model of uncontrolled full-wave rectification. When node A is positive with respect to node B, the diodes D1 and D3 conduct. The direction of current in load is downwards. During the negative half cycle of AC, the node A becomes negative with respect to node B. The diodes D2 and D4 now conduct. The direction of current in load is again downwards. Hence, in both cycles, the direction of current in load remains same. Controlled rectification is the basic principle of DC drives, for which thyristors are used. In the bridge configuration, a same pulse is applied on 2 thyristors per half cycle of AC. The control angle of pulses determine the amount of power transferred. Firing angle is monitored using a separate scheme like PWM. According to the following diagram, when node A is positive with respect to node B, the thyristors D1 and D3 will have forward bias condition, but they will not conduct till any gate pulse. So, when D1 and D3 are fired together, current flows through the circuit. Similarly, in the negative half cycle of AC, the thyristors D2 and D4 are fired at the same time, which results in conduction. The resultant output is unidirectional, but with fluctuations. You can clearly observe the dependence of output voltage on the firing pulses of thyristors. This is the basic simulation of a DC drive in which closed-loop speed control with inner current loop and field weakening has been shown. Let us analyze this diagram. The DC motor is coupled to a techo generator, whose output is fed to a filter to reduce harmonics in the current, and convert this current to actual equivalent speed. This speed is compared to desired speed. The difference is then passed through speed controller and current limiter, which convert that difference to equivalent current, and then generate a value of reference current, respectively. On the other hand, the actual current that is being fed to the motor is measured, filtered to remove any harmonics, and then compared to the generated value of reference current. Now, this difference is passed through a current controller which specifies the firing angle according to the difference and send a signal to the firing circuit. From here, pulses are applied to the controlled rectifiers at calculated intervals. In this way, we control the amount of power applied to the armature of motor and hence control its speed. Below the base speed, the motor speed is controlled via inner current loop, while above the base speed, the same is controlled using the field weakening. For the field control, first, the EMF generated by motor is calculated. Now this value is compared with the reference EMF that should be generated by the motor according to the specified speed. The difference is then fed to field controller, actually a current controller, which specifies the firing angle for field rectifiers. Hence, the power supply to field is controlled. At Tetra Pak Lahore, Eurotherm DC drives are being used which work on the same above-mentioned procedure,